Hello everyone, welcome to lecture 2. In this lecture, we're going to talk about several topics. One is the symbolic manipulation, one is the graphing and the compositional functions, and also the linear function itself. So let's dive in. When it comes to symbolic manipulation, we often talk about re-expressing the same expression to facilitate our analysis. So this actually takes on a few flavors. Now, let me just change the color. See, we have a function that looks like this. So 2 times 3x squared minus 2x plus 5. So this is one part, and plus another part, which is x squared plus 3x minus 7. Now, this expression looks a bit complicated, and we can do something to simplify this expression. So what do? We can we have this multiplier. We can multiply it to each term inside the parentheses, right? So we can just plug in, and we have 6x squared minus 4x plus 10. And we can expand the term as well, remove the parentheses. And now we can do additional manipulation so that the form is further simplified. So I see that 6x squared, x squared, it becomes 7x squared. And then this term add together, we have the minus x, and we have the plus 3 as well. So this is just a simple illustration of how we can do the symbolic manipulation. On the other hand, we can also do something called factoring. So factoring means that when we look at expression, if there's a common factor, we can extract it out and then re-express the same thing in simpler terms. So what do I mean? Let us look at a simple example. So see, we have this expression here, 3x squared minus 3x minus x plus 1. So if we just look at these terms now, usually this actually takes a bit of trial and error, but say let's take these two as a group, and then this as a group, so can express as 3x times x minus 1, because 3x is their common factor. And also because I have this x minus 1, so I know that if I can express in this way, it'd be easier for me to proceed. So now this actually becomes another common factor. So we can continue 3x minus 1 and x minus 1, which is multiplied together. So this is actually a very common practice to use the symbolic manipulation so that this form is actually easier for our analysis. Now let's continue. So if we have this form, right, there are some benefits. For example, in this case, we know that if this term is equal to 0, then we know that either 3x plus 1 is equal to 0 or x minus 2 is equal to 0. So of course, we can solve for x. In this case, in the first case, x equal to negative 1 over 3. In the second case, x equal to 2. Right, so this actually, because we performed the factoring, then we know that this is a solution for x, two possible values. Right, so one slightly more involved case is on the right one. So we have both the denominator and the numerator that needs to be simplified. So for the first case, for the numerator, we can factor as this way. So 2x plus 1 times 3x minus 1. So how do I do this? Because we know that 6 can be decomposed into 2 times 3, and 1 is 1 times, so the negative 1 is 1 times negative 1. So there are these 4 possible terms, and through a bit of trial and error, you know that this is the result of the factoring, and we can actually expand it back into for example, if we expand it out, then 6 squared x squared minus 2x plus 3x minus 1. So it takes a bit of trial and error, so you can just write one version of results and then expand it back to say if it equals to the original form of the expression. In this case, it is. Right, so we have this factoring results in the numerator, and we can do the same for the denominator, which we can express in this way. Right, so now this is where we're at. We are looking at the common factor, this term, to x plus 1, and the same term in the denominator as well. So this is a signal that we can further simplify by canceling this common term out. So, well, this is our simple results. And because we did the cancellation, and we need to add a condition, which is very important. So the reason why we are able to do this is because 2x plus 1 cannot be 0, which means that x cannot be negative 1 over 2. Right, so this is actually an important condition we need to specify in our derivation. So that's the benefits of factoring, and a lot of times you'll find it helpful to actually do a bit of algebraic manipulation so that it's actually easier for your analysis. Now, let me do a bit of more in-depth analysis. So we know that earlier we have this a few critical points. So a critical point is nothing more than the value that's making the value of this original expression a bit more interesting. So the critical value could be when x is equal to 1. So if x is equal to 1, then of course this denominator does not stand, so it cannot exist. And another interesting value could be x equals to negative 1 over 2, which is what we did just now. And also could be the numerator is equal to 0, so 3x minus 1 equal to 0, then x equal to 1 over 3. So these are the potential critical values that we would normally be interested in, because that sort of determines the shape of the function. So now we just take one negative 1 over 2, 1, and also another value to see what is the results of these two expressions. This is the original form, this is the simplified form. So if we plug in the x equals to negative 1 over 2, then we know that because x cannot be 1 over 2, right? So then this will get an error, so cannot proceed like this. So that means that if we take x equals to 1 over negative 1 over 2, then there will be an error in the calculation, right? However, if we're taking this value and plugging this form, then we can get some results. So we can just plug in and then do the calculation. The results turns out to be 5 over 3, right? So this stands because now this form does not have the restriction that x cannot be negative 1 over 2. So that's another added benefit. What if x equals to 1? Now, in this case, because we know that for the original form, it can be expanded to be simplified to this form, then of course we know that x, for this to stand, x cannot be equal to 1. Right? Otherwise, it will not exist. So in this case, we'll get an error as well. Similarly, this will also get an error, right? So this will we have the values that we cannot plug in and do calculation. Now, for the last case, when x equals to 2, now we can just plug in, do the calculation, and then see that this is equal to 5. This is again equal to 5 because they are essentially the same expression. Is only the restriction is different, right? So this is a bit more in-depth analysis. Let us look at how to graph a function. So when we talk about graphing a function, several things that come to mind. First thing is for the simplest approach, we can take different values of x and the values of y or f of x. So if we say if x is equal to 0, then this would be 1. If it's 1, that'd be 3, etc. Let me take another value. If it's x equal to 2, that would be 5. So naturally, if we draw coordinate system, this is x, this is f of x, then we can say this is 1, 2, 3, 0. And we can draw simply, for example, 2, 3, 4, 5. 1, 2, 3, 4, 5. So now let's draw each point exactly as they are. So first point, this is gonna be this first point, the 0, 1. So I take 0, I take 1. So this is the first point. Second point, I have 1, 3. So 1, 3 goes to here, right? And the third point, 2, 5, 2, 5. So this graph is obviously not drawn to scale, but just to illustrate a point. So at this point, you know that already when we are looking at a linear function, right? Think about question, how many points do we need to determine a linear function, which is a line, right? So to draw a line, we just need 2 points, right? So for example, this point and this point, then we can draw a line. So this third point is actually optional, but we just drew it here for illustration purpose. So in other words, a straight line, which is like this, is a function, it's a straight line. This is uniquely determined by just 2 points, right? It's not like a curve, we need many more points. The other thing is, how do we calculate the slope of a linear function? So we talk about a linear function, then there are a few interesting characteristics we can use to sort of characterize the function. One is the slope. The slope, we can do the calculation by taking any 2 points. For example, if we take these 2 points, then we know that the formula is like, if we denote slope as m, then we can take the first point's y coordinates minus the first point's coordinates, and then also the x difference as well. So this is to take any 2 points. In this case, if we plug in these 2 points, then we can say if this is x2, y2, this is x1, y1, right? We just take the value as they are, and you can see that now this becomes 3 minus 1 divided by 1 minus 0, which becomes 2, which happens to be this guy, right? So, and it's not a coincidence, but it's by contrast should be the slope. I can also, so the 2 here is actually very special. It is actually the slope of the line, right? So this is the slope of the line, and it's equals to 2. And the formula to calculate the slope is exactly this. So we have 2 points. We can just take the division of this y coordinates divided by the x coordinates difference. This one is also another interesting characteristic. It's called the intercept. Intercept. It is the intercept with the y-axis, which is this point, right? So which means that if x equals to 0, then y would be equal to 1, right? So the intercept is always looking at the case when x is equal to 0. So this is how we would actually look at graphing a function. We can take different values, or we can just take the intercept, which is at this point. So we have this handle, the anchor point at the y-axis, which is intercept. So find the intercept and then find the slope to say how sort of how the slope would be. Could be like this, could be like this, like this. So in other words, if we have the intercept and we have the slope, now this also uniquely determines a line. So that's actually the same as if we have just 2 points, because we can calculate both the slope and the intercept from these 2 points. All right. So that's just a bit of analysis. Now we can actually look at more closely what is the slope of the line. Okay, we know that is already the formula for calculating the slope. And if I just draw a line here, right? So for any line, we just take any 2 points. So this point is the x1, y1, and this point is x2, y2, right? So now we have this triangular here. What we're doing in here is graphically represented here. So we can take the vertical the difference y2 minus y1 divided by the horizontal difference x2 minus y2, and this is the division of these 2 terms gives us the slope, right? A bit of discussion on different forms of function, right? So a function can be the slope-intercept form, which you already know. So if we denote slope as m, and then this our x variable and plus b. B stands for the intercept. So this is one form, which is called the slope-intercept form. So we have the slope, we have the intercept, which are constants. So constants meaning they are specific value. It could be 0.1, could be 10. Right? So any value, as long as they are constants, they are fixed. X, on the other hand, is called a variable, right? A variable because it would vary, it would change. And we have another variable, which is y. So we're using this form to describe the relationship between the input x variable and the output y variable. Right. So there are many cases in real life. For example, S could be the number of products we produce in the market, and Y could be the corresponding price for this product. So you have more price than more products, then of course, given the supply demand relationship, then the price could go down because now you have more suppliers. So this is actually a very common form to describe some relationship or some patterns in real life. Now, this is just one form. Another form would be the point slope form. Let me just write down point slope form. This is the slope intercept form. So when it comes to the point slope form, of course, we will take one point, which is we denoted by x1, y1, and we can just write down the form of the linear function as this. So y, which is a variable, minus y1, which is a constant, equals to n times x minus I squared. So this is also assuming that we have calculated m already, and then now this is time to get the form of the linear function. So this form is actually what we do often use. So to get the form of the function, and it also depends on whether you like the first form or the second form. So, but when it comes to the calculation, the second form is actually more handy because we just need to calculate the slope, and then we can just take any point, which is this one, and then plug it in the form. So that's the second form. Another more general form, which is so-called a standard form. Standard form would be like this. So uppercase A x, uppercase B y equals to C. So A, B, C are just nothing more than constants, can be anything, and then we can express in this way. So this is another form which we just need to take note of, right? Now, a bit of insight from a function perspective. So if you look at x equals to x squared, then we can draw it out. This graph is like this. So when we talk about the slope, right? We would often associate with the velocity, meaning is the function increasing or decreasing? So if the slope m, right? So if it's positive, then it means that it's increasing. So the function is increasing like this. So on the right half, the function is increasing. On the left half, the function is decreasing. So the slope is actually an indicator of either the function is increasing or decreasing. Now, if we do a more in-depth analysis, we take another sort of slope of the velocity, then it actually gives us the so-called acceleration. Acceleration means, are we increasing at an increasing speed or decreasing speed? Right. So that's a bit mouthful. Graphically, we look at on the left half, on the right half of the graph, we see that's the slope. If we take this point, is like this, and take another point, slope is like this value. So of course, as we move from left to right, the slope, the value of the slope is actually increasing. So it's actually accelerating in terms of a speed. So the speed gets faster and faster, and also the rate of change itself, which is the velocity is also increasing, right? So this is the sort of another derivative of the slope itself. And of course, here we have the if we move from left to right, and then of course this acceleration is decreasing. So in other words, now velocity gives us an indication of whether fx is increasing or decreasing, and the second derivative, which we're going to talk about later, but essentially the slope of the velocity, which is termed the acceleration in this case, is looking at either fx is increasing or decreasing at an increasing or decreasing speed or rate. So that's just a few notions to bear in mind. Right, so common types of functions. We have the, for example, the most common type is called the identity function. Just draw it here. So this is the identity function, which is y equals to x in this case. And we can look at the domain as the range of each functions. So domain would be all real numbers. So just sometimes we write it as R, right? So R stands for real numbers, or sometimes we write to from negative infinity to infinity. So which is either works. And then the range itself is actually also from negative infinity to infinity because it can take on any value. We can also look at the square function, which is y equals to x squared, which is the case we just looked at earlier. And then, of course, in this case, x can be anything. But y index, it has to be positive, right? Positive in this kind of expresses like take on the value of 0 or even greater, right? So this is the another common function. So we also have the cube function, which mathematically looks like this, and then if we draw it graphically, it's actually increasing very fast as x becomes bigger, or decreasing very fast. So, and as usual, we can have this domain, which is taking on all the values, and also the range of, or the value of y is all the range of values. So we also have the square root function, right? So square root is as the effect of squaring, right? Taking the square root to x. So which means that if x becomes bigger, then it's actually being more severely punished. And this is the what the graphs look like. And in this case, we see that x itself, which is the domain, cannot be negative. So you can only take on the value of 0 or positive. Y in this case is also the same because I cannot go to x cannot go to negative. So this is the domain and this is the range. We also have the absolute value function, which is taking the absolute value of x. And if you look at comparing in this with this case, then of course the negative parts will become positive. So if you draw the graph, it'll be like this. So naturally x can take on any value, but y in this case can only take on the positive or become 0, right? So these are the common type of functions. And another topic is about the vertical and horizontal shifts. So if you look at any function, take the example of the absolute value, right? And then vertical shift means that the function itself will move up or move down. So if we move up, then this will be changing the value of y itself. So it could be, for example, y equals to square plus 5. So this is so-called the vertical shift because it's changing the value of y. However, if you look at the horizontal shift, right? So this is shifting towards the right, and then, for example, this form could be, if this is 5, then the end result be x minus 5. That's why is because x needs to take on the value of 5 in order for the value of y to be 0, right? So so if you just look at the expression here, adding a positive number would shift the curve, the graph of the function. If it's positive, then if it adds to the value of y, then it's actually shifting upwards. However, if we want to shift the graph towards the right, then we need to minus of 5. So that's actually something just to keep in mind. All right, so that's it for today.